Welcome, everybody, to an evening about quantum computing, one of the most difficult subjects you can imagine. But luckily, we have very good speakers tonight, so hopefully, you will leave this theater with a lot of knowledge about quantum computing. As you might have heard, in the beginning of this year, Microsoft launched a campaign. And they highlighted their Majorana chip, Majorana 1 it's called. That's a quantum computing chip, not an ordinary chip, but a quantum chip. It's a possible building block for a quantum computer, and it uses Majorana states to calculate with. What Majoranas are will be explained in a few moments. But there are other ways to build quantum computers, other ways to build qubits, so that's the bit, the quantum bit of a quantum computer. You can build qubits with photons, electrons, Majoranas, and perhaps even other particles. So there are many ways to build a quantum computer. This evening you will hear a lot about these building blocks, and you will hear especially what we are building here in Twente. We're very curious about that. But we will start with what is quantum computing, how did this field of science and technology evolve, because it's a very developing topic. I am very, very happy that we have four specialists in our midst tonight. I start with Esther van der Loch. Esther, you won't be presenting this evening, but I want to mention you. You're a PhD candidate in the field of nanoelectronics, and you helped preparing this whole program. Then we have Femke Witmans, sitting over there. You're a postdoc in the field of quantum electronics. That's a field we need, and you built a special wire which can be used in a quantum computer, but you will explain that later. Then we have two full professors. Please come in and find a seat. Two full professors. Floris Zwanenburg, he holds the chair of quantum electronics at the UP, and Alexander Brinkman, who is a chairholder of the chair Quantum Transport in Matter. You are all involved into quantum computing one way or the other, and will explain how we can build quantum computers. I want a big hand for Esther and Floris, starting the first part.
Yeah, so thank you all for being here. So maybe you're already a quantum enthusiast, or do you want to learn more about the wondrous world of quantum? But at least we hope that after tonight you will think back about these dialogues when you hear something about quantum technology, for instance, in the news.
Yes, and as Peter already said, the night is divided in two parts. First, Femke and myself will tell you a little bit about the history of quantum computation, what can a quantum computer do, what do we need to build it, and what are the different ways we try to build it in the field. After half an hour, there's also directly the opportunity to ask questions for all of you. So that directly gives you a short break, and then part two starts, which focuses on the Majorana hype, Majorana qubits, and Majorana physics, which we find most interesting.
So to start off, maybe, Floris, do you understand quantum mechanics?
Yes, of course I understand quantum mechanics. I'm a quantum professor. But actually, if you listen to this famous quote from Richard Feynman, then maybe this is not a wise thing to say. I think I can safely say that nobody understands quantum mechanics. And the quantum theory predicts very well what happens in quantum experiments, what we see so far. But the implications are extremely difficult to understand. They are so counterintuitive that it's difficult for our brain to process this. Like quantum tunneling, like the uncertainty principle, like entanglement, as Peter already said, and also superposition, right, Femke?
Yeah, so superposition is a topic that we will discuss more often tonight. So what is superposition actually? We can think about this in an experiment that Schrödinger actually thought of. So he designed a thought experiment in which he put a cat in a box with a little bit of poison in a bit of glass. And then he closes the box and he says, well, we now don't know if the cat inside is alive or dead. So we can as well say it's alive and dead at the same time. Now, this is of course a very large object, a cat, but on the small scale, these laws of quantum mechanics actually hold up, and we can describe them by a wave function. So the wave function is, we write that down as here on the left, but the wave function of this Schrödinger's cat we can describe as partly dead and partially alive. So this is what we call superposition. Now, as said, for cats this doesn't hold, but as something is small scale as the electron, this does hold. You might have heard of the wave-particle duality of an electron. The electron can be both a wave and a particle at the same time. And to illustrate this, we can also talk about the duck-wave duality. So here we have two ducks in a pond, so two particles in a pond, and they also make a wave around them. And you see that these waves interfere with each other. So the two waves around the ducks, they make an interference pattern where the waves are higher at some points, those are the maxima, and are lower at some points, the minima. And we can see this in a different video as well. Maybe you want to introduce this?
Yes,
Floris?
please. Yeah, so for water, everyone can easily visualize this, right? The picture is clear. But this also holds for light, and that was first done in an experiment by Young around 1800, where he did interference with two light sources. So we see on the screen here two small slits in the screen, and from that we get two circular sources of light that come out of the two slits. So we see they're circular in shape, but of course these two wave fronts that go out in this circular shape interfere with each other, right? And what you then get is constructive and destructive interference. So if you have the peak of one wave and the bottom of another wave, they cancel out. And that's what we see if we continue the screen. Then we get some parts with maxima and other parts with minima. And actually, if you look at this pattern, you see some kind of straight lines appearing, and that's where we indeed get this destructive interference. We weren't aware that this sound was also in this movie. But this is a clear example of interference of waves, and this showed that light behaves as waves. Later, it was also shown that light consists of photons, of photonic particles. So it's a particle and a wave at the same time. Can you process that? But the same holds for electrons. Electrons are the smallest particles in a current, in an electric current. And people have done the same double slit experiment as with light. They've done it with electrons. So what we see here in the upper left picture is the screen on which individual electrons that have gone through one of those two slits collide with the screen, and they appear as small spots, as individual particles. Therefore, you would say electrons are particles. They're like little balls that go through one slit or the other. But as long as we continue to shoot more of these electrons through the two slits, we see that more and more particles appear. But finally, in picture D, in the bottom right, we see that the sum of all the collisions of all the electrons with the screen still builds up to this interference pattern. We see maxima and minima. Therefore, all the electrons do not only behave as a particle, but also as a wave. So that means that they go through both slits at the same time, as a wave would do. Of a wave, I can imagine it, but of a simple ball, this is unimaginable. So that's the wave-particle duality.
Yeah, so all this quantum theory that was thought of about 100 years ago. So here you have a picture which you might know, and it's a very famous picture because all the big names that contributed to quantum theory are actually in here. So you see Einstein, for instance. So this is a game of find the expert. So here we have Einstein, but also Marie Curie, and they all contributed to the birth of quantum theory. But still nowadays we use these theories of quantum mechanics to do the experiments in the lab that we do today. So what fascinates you about quantum mechanics the most, Floris?
Well, what excites me most is actually the fact that we can observe things that we can never see with the bare eye. And for that we need nanotechnology. So what you see here is a photo of myself in the clean room 20 years ago when I was a PhD student. And in the clean room, we fabricate nanostructures that are already impossible to see with the bare eye, but you can see them with a microscope. Then using that, we could finally do our quantum experiments. Here you see me performing an experiment in Australia where I did a postdoc. And here I was observing individual electrons. So we could put electrons in a Schrödinger cat-like box and showed indeed that they could be in two positions at the same time. So first of all, it's extremely cool that you can see something that you will never be able to see with the bare eye, the electron. But also specifically in this experiment, we measured the spin of an electron. The electron also has a small magnetic field, but it is so tiny that you are unable to measure that magnetic field. In this experiment, however, we could load a single electron in a box, in a cat box, and we could show that it was either spin up or spin down, as you can see in the cartoons on the left, and the actual measurements. So to be able to measure something that is basically unmeasurable, that is the coolest thing you can do, I think, in the lab. And yourself, Femke?
Yeah, so for me as well, that we can do things in the lab and it's kind of counterintuitive, but still we can explain it with the quantum theory. That's what excites me the most. And here you see some pictures of me in the lab because that's what I actually love doing the most, being in the lab, fabricating devices and measuring them. But it also relates a bit to the application. So the fact that we are maybe working towards something that can be bigger than what we do from day to day in the lab, that's also what drives me. So here on the right, you see a picture of these three guys who invented the transistor in 1947. And I think they didn't know at that time that we would walk with our phones in our hands and we could send prompts to AIs, and that this is the basis, based all on these transistors that they invented. So that's something that I find, wondrous to think about, that quantum could also have these cool applications.
Exactly, and that's of course the great revelation of the classical transistor, right? That led to classical computing, and that allows us to have a computer in our pockets, our phone, that is stronger than the first computers that were built in the 1970s, 80s, and even 90s. But what kind of quantum applications should we think about of a quantum computer instead of a classical computer, Femke?
Yeah, so you indeed, for quantum technology in general, we can think of the quantum computer, for instance, and the quantum computer could break our ways of securing our data or our banking. And for that, we can also use the same quantum technology to also secure this data better. For instance, by quantum internet or by quantum security in general. But specifically for the quantum computer and what it could bring, we can think of three main applications entailing, for instance, material science for better energy consumption or lower energy consumption, applications in health where we could personalize medicines, or by making climate models to see how the climate develops over time. All these things a quantum computer can calculate more efficiently than a regular computer could do right now. But where does this strong quantum computation come from, Floris? Do you have an idea?
Well, maybe you can tell me.
Okay.
Or can you tell me how it works?
Yeah. Shall we try to do this analogy with a maze?
Let's do an experiment.
Okay. Alexander can bring a maze for us. So here you can already see the maze. We're going to solve the maze. So if we were a classical computer, then we would have a ball in a maze, for instance, this one, and the ball would try to exit the maze one position at the same time. So it would first try this one, and then see, no, this doesn't work. This is not the exit. And then try the next one, no, doesn't work, and it takes a lot of times. But now if we use a quantum computer, then it is as if we're going to fill this maze with water, or in our case, lemonade. Okay, so I hope you can see this. We're going to...
We've not tried this.
We have not tried this. This is an experiment in real life right now. Don't do this at home, indeed.
Need a hand?
And I hope we have enough lemonade. But now you can see that the maze fills up, or at least I hope you can see it. And It tries multiple paths at the same time. It's leaking.
There's
Oh
some
no.
quantum errors there in the bottom. Well, I disagree, Peter.
Yeah,
Let's see where-
now it's going to
You have
leak
to ask
here.
the right question.
Oh,
yeah.
no.
Oh,
Oh, it's starting to leak here as well. Okay, as you can see, this is also what happens in
oh, now it's really
experimental
working.
weird. Yay!
Yes.
It's found the exit. Amazing. Okay, maybe I can put it a bit like this.
This reminds me of secondary school, where your physics teacher does an experiment in class. So clearly, we're not yet ready to become or we are ready to become a real physics teacher.
It
So
does
what this
smell like
shows is
apple.
that where a classical computer has to try all the different outcomes, like going through the maze one attempt at a time, a quantum computer is like water. It basically goes through all holes at the same time, through all possible solutions. And that's why it can instantly find the solution to a maze. That's what we call quantum parallelism. And while and that's so it's for quantum computing you use different algorithms, right? So you have to ask a very specific question to get the answer you need. And that's a bit more complicated. For that you need different kind of algorithms, not classical algorithms, but quantum algorithms. And we'll give you an example in a little bit later. All right, Femke, well done.
Yeah.
We survived.
We survived the floor, hopefully as well.
Yeah.
Yeah. Where does this high computing power come from? And then we have to look at the smallest building blocks of the computer, actually. So for a regular computer, we have the smallest building block is a bit, as Peter also mentioned already. This bit can be 0 or 1. Now for the quantum computer, this is a qubit, the quantum bit. And for this we also have an analogy. So think back of this wave function of Schrödinger's cat. So we had the Schrödinger's cat wave function where the cat could be alive and dead at the same time. Now we can look at a different superposition as well. For instance, of a coin, where head is the 0 and tails is the 1. But now if we spin the coin, then the coin is actually 0 and 1 at the same time. We don't know what the outcome is. We don't know what the measurement outcome is. And this is also how this qubit works. But now not of Schrödinger's cats or coins, but of electrons, for instance. So here we have an electron sitting on the left side. Here we have an electron sitting on the right side. But we can also visualize this in a way where the electron can be partially on the left side and the right side. So in PowerPoint physics this looks nice, but how can we actually make superposition in real life, Floris?
Yes, so for that we need some kind of quantum mechanical two-level system. So something that's quantum mechanical and that has two different states. For example, the simplest example is indeed that electron that can be on the left or on the right, where one of the states is, for example, the logical 0, and this is the logical 1. So if it's in the superposition, it's 0 and 1 at the same time, our quantum superposition. That's called a charged qubit. Then we use the charged state of the electron as the information of the quantum bit. But there's many different kinds of quantum bits, as we will see later today. One other example is the superconducting quantum bit. And what you see here is a cartoon of a ring made of a superconductor. And the ring has a few intersections, which you can see indicated in the bottom left. These are Josephson junctions. And in this case, the quantum mechanical state that gives you the qubit states is the magnetic field. So maybe you remember from secondary school physics, if you have a current going through a ring, it gives you a magnetic field perpendicular to the ring. And if the current goes the other way, then the magnetic field also goes the other way. And that's exactly what we see in this cartoon. So we have two circulating currents, one counterclockwise and the other counterclockwise, and they give two opposite magnetic fields. And in this specific superconducting ring, with those so-called Josephson junctions, we've got these two currents in both directions at the same time. Therefore, we have two magnetic fields at the same time, this superposition of two quantum mechanical states. Right, so we have what you would call a spin-up state, or a magnetic field up and a magnetic field down, or a superposition of magnetic field up and magnetic field down. Right, so we look for a quantum mechanical, what we call two-level system, two states. And here is a whole set of examples that people have been studying in the last 20, 30 years or so. People have been studying individual atoms, of course, the smallest amount of matter that we can study. People have used electrons and superconducting loops, which you can see here in the middle row. People use spins, so these magnetic fields of a single electron or of a nucleus, but also topological states, as we will talk about in the second half of tonight. And even photons, as we study here in Twente, in the photonic quantum computer, and one of our photonic professors is here tonight in this talk as well. At least he's in the audience, sorry. So most success has been reached so far with the superconducting qubits. You may have heard of the 1000-bit quantum computer of IBM. That's with superconductors. Today we'll say a little bit about the spin qubits, which we study here in Twente, and also in the second half on the topological quantum bits. And we will not say anything about the photonic quantum computer here today. That's been discussed in a previous Studium Generale lezing. But Femke, can you find another way to say how we can actually, why does this quantum superposition give us so much more calculation power, computing power?
Yeah, I can tell you a little bit about that. Maybe I can tell you even a story about it. So the story is about the inventor of the chessboard, and it's about exponential growth. So there was, once upon a time, there was a king, and he wanted to reward the inventor of the chessboard for his invention. So he asked the man, what reward would you like? So the humble inventor said, I just want 1 rice grain on the first square of the chessboard. And the day after, I want that amount doubled. And then on the third day, I would like to have that value again doubled on the third square, and so forth. So the king easily said yes, because he didn't know what implications this would have. But then still on square 7, it's quite doable to have this amount of rice grains. But if we look at square 10 already, then the king needed to lay down 512 grains of rice. On square 20, he already had to lay down more than 500,000 rice grains, and on square 24, more than 8 million. Well, as a chessboard has 64 of these squares, you can imagine it counts up real quickly. Now, this holds for the quantum computer as well, not with rice grains, but with qubit computation states. So if we have 1 qubit, like on the first square, then we have 2 possible computing outcomes. So the qubit can either be a 1 or a 0. If we have 2 qubits, then we have 4 possible outcomes: 0, 0, 1, 0, 0, 1, or 1, 1. 4 outcomes. Then on the third square, this again doubles. So you can see that as with the rice grains, we have more outcomes, more measurement possibilities with these qubits. And yeah, that's where the high computation power comes from in the quantum computer. But how many of these qubits do we actually need to make a quantum computer?
Well, we need many. So maybe some of you have heard about D-Wave, a company that already makes a quantum computer. However, this is what we call a quantum annealer, and it solves optimization problems that a normal computer can also solve. So this quantum computer is not what we are looking for. We are trying to realize a universal quantum computer, or actually in our field. And that would need about 1 million working quantum bits. And the state of the art currently is 1,000 quantum bits. So we're far from there. So I'd like to speed up a little bit because we have 5 minutes left, Femke.
Oh, that's not
yeah,
too much.
We're going fast. Okay. And we're going to do a short and maybe brief, I would call it, history of quantum computation. Right. So this field was kick-started by Richard Feynman in 1981, when he first said we should be able to make a quantum computer. And he, yes, thank you very much. And he said in his paper, we can use quantum computers to simulate quantum systems that are too hard to simulate using conventional digital computers. And it was about 13 years later that Peter Shor for the first time made this quantum algorithm that I alluded to earlier. And this algorithm is a specific quantum algorithm, and it can efficiently factorize, as we see in the upper right, a number in its prime numbers. And of course, for small numbers like 15 and 91, this is relatively simple. But for larger numbers, it becomes exponentially more difficult, where even for very large numbers, on the order of 10 digits, a classical computer cannot solve this efficiently. But with Shor's algorithm, a quantum computer can do it. And this was first demonstrated experimentally already 8 years afterwards, which I'll tell you in a little bit. So this was the start of the field of quantum theory, which started in the mid-1990s. And in the same conference, there was also here in the upper right, David DiVincenzo. And David DiVincenzo, he formulated the criteria for what you would need to realize a complete quantum computer for the physical implementation of quantum computation. These are now called the DiVincenzo criteria. And you see one of them, for example, you need to be able to do a qubit-specific measurement. That is the readout of the spin that we showed earlier this evening. And the other criteria are that we, for example, need to have long-lived coherence times. We need to keep the quantum state in one piece and not destroy it before we've done our calculation.
We don't want this leakage over here.
No leakage, we want to have pure states, indeed, yeah. So in 2002, this Belgian researcher, Lieven van der Sijpen, demonstrated the first experimental realization of Shor's algorithm. And he let a 7-qubit molecule, he made it into a 7-qubit quantum computer, and he let it calculate that 15 equals 5 times 3. Now that's first of all funny, because a Belgian can get a PhD degree by calculating that 15 equals 5 times 3. So it's nice for us Dutch to make jokes about this. But of course the real feat is that this shows that for the first time he made a mini quantum computer and he let it work, and he shows that this quantum algorithm works. So this kick-started a worldwide race towards the first quantum computer. And that's what led to all these qubits that I talked to you earlier about. So there's all these qubits that people study worldwide with atoms, electrons, spins and photons, and even companies have gotten on board. Big companies like Google, Intel, Microsoft, IBM. And that's now the race we are in. Let's see what we're going to do, Femke.
Just continue with you.
Just continue briefly?
Yeah,
Okay.
yeah.
So the first superconducting qubits were made in the middle 1990s by partially Hans Moyer on the upper right, the godfather of Dutch nanotechnology, some would call him. And they made the first quantum bit and also the first coupled quantum bit on the left. So going from 1 to 2 qubits in a few years' time. And then in 2018 or 2019, the group of John Martinez showed for the first time that they could make a small quantum processor of 53 quantum bits that demonstrated what is now called quantum advantage. And John Martinez got the Nobel Prize last year, partially because of the results that he received here. So that summarizes how we went from 1981, the first conception of the idea of a quantum computer by Feynman, to where we are now, the 1000-qubit superconducting quantum processor of IBM. So a lot happened in this time. Femke, would you like to compare this to...
This reminds me of the evolution of the transistor, actually. So if we look over here, you see these men, again, that I showed in one of the first slides too. They invented the transistor in 1948. But it actually took quite a while before we are where we are right now. So it was 1948 when they invented the transistor, but the transistor that's actually nowadays used a lot is the MOSFET transistor that's invented in 1959. So here you see that we first had one prototype transistor, but the actual speed up was only until 1959, until the first usable transistor was invented. And after that, it took still quite a lot of time to have a lot of transistors on one chip. So as you can see, Floris is holding one of these wafers. And this is a wafer that's produced in chip factories to actually make the chips that are in our phones nowadays. And on this wafer, there are multiple chips with thousands of these transistors, but they all fit on this on this wafer. So we can compare this to the evolution of qubits as well. So we can see here that for the transistors, we went from 1947 with one prototype transistor to 2005, where we had 1 billion transistors on a chip. Now, in superconducting qubits, there was one qubit in 2004, and nowadays, or at least 2023, we are at 1121. So now if we look at spin qubits, which is more the field that we are working on here in Twente, or at least in Floris Group, then the speed up is maybe a little bit less fast, but still, in 2005 there was 1 spin qubit, and nowadays there are 4 spin qubits coupled in germanium, which is actually a nice parallel because the first transistor was made of germanium, and now the spin qubits are also made in germanium. So what do we do in Twente then? Maybe you can
Briefly, so we hope to use this kind of technology where we can make 1 billion transistors on a chip to later also to catch up with the superconducting qubits, right? We have this technology in-house, and if we can make 1 qubit or 4 qubits, we hope that we can more easily make 1 million qubits 10 years from now. So it's not yet clear which prototype will be in the real quantum computer in 20 years. And in Twente, in my team, we again use the facilities of the Nano Lab, the big red building you may have seen here, to do the processing you see our PhD student Dennis doing here on the left. He holds a small wafer of only 10 centimeters, so that's a baby wafer compared to this one we have over here, to make the nanostructures like the one here in the center that Femke has made. We see a thin Tellerite nanowire, which is 1,000 times thinner than a hair on your head. But we can process those and, as said, make electrodes and measure these kind of devices. So we have to make them extremely small and then cool them down to extremely low temperatures. What you see on the right, this is one of our dilution refrigerators, a cryostat that can help us reach minus 273 Celsius. We need to make things extremely small and cool them down to extremely low temperatures to see quantum effects. We also think that a future quantum computer will operate at these kind of temperatures. So we make these structures and then we do experiments. For example, study single atoms in silicon, or study germanium silicon nanowires, both cubic and hexagonal, which can have advantages photonic properties, and also the Tellerite nanowires in the bottom right that Femke studied during her PhD. And this allows us to, for example, again, indeed observe individual electrons, as you see in this experiment on the right, where we can have a high signal giving us, showing us that we have no electron, or a low signal that we see here in the bottom in the blue, that can show us that we do have an electron bound to a single bismuth atom. This is an experiment that we do in the lab, and that helps us to, again, observe things that are not observable in bare eye on a day-to-day notice. So with that, we'd like to close this part of the session, and I'd like to give credit to all the people in my team, the PhDs and postdocs, who do all the magic in the labs, in the nano labs and the measurement labs, and help us to try and observe new states of matter, new quantum states in the lab. So thank you very much for your attention.
Thank you. I have to
Sorry,
watch out
Peter.
for the quantum lemonade
Yeah.
on the floor, but it was a brilliant metaphor for how a quantum computer works. So not one ball looking for all the possible exits, but a fluid at one moment, parallel finding its way out. That was a very nice. You thought this metaphor yourself, I think. That's, yeah.
We just need to make it leak-free, just like the most qubits
Yes.
are still sensitive to decoherence. Our
Thank you very
maze
much,
still decoheres as well. Yeah.
Anneke, for clearing up the mess. Otherwise, we will stick to the floor. Okay, we have time for questions, about 10 minutes. I see a hand already, and I take the microphone. Just a second. So, here you are.
Yes,
I think
thank
it's
you very much for your very interesting presentation. It's kind of mind-puzzling if you try to understand what's happening, as you already warned us for. But I have one question on superposition. The analogy with the cat in the box, where you say it's dead and alive at the same time. If you open the box, it's either dead or alive. So observation stops the how do you call that, the rare state of superposition. And how do you deal with that in the qubits that you are trying to build? Because if you watch individual electrons being in a potential superposition mode, you can't watch it because it's either spin up or down.
Exactly. That's why you cannot read out the qubits until the complete computation is done. And that's also the difficulty, as the gentleman here alluded to, is that you have to ask the question first to your quantum computer and then finally read out the state to get the specific answer you're looking for. Reminds me a bit of the Hitchhiker's Guide to the Galaxy. The answer is 42, But what is the question? But clearly this solution to Shor's algorithm tells us that we can indeed solve specific problems if we know the question in advance, like what is the prime number of 15? What are the prime numbers of 15? Yeah.
Thank you very much.
Yeah. And you need to cool down this whole device for noise and things like that.
Noise is
interference,
the simple way of seeing it, but
Yeah.
but anything that can interfere with our device can disturb the quantum state. That's what we call decoherence.
Okay.
Yeah.
Then the wave collapses.
Yeah, it's similar to measuring.
Yeah.
It's basically
Yeah.
you measure it on purpose, partially, you could say. Yeah.
Yeah. Okay.
So the pure state is no longer pure.
Yes, I see. There you are.
So the physics is interesting and the hardware is interesting, but what about the software? So how does one program a quantum computer?
Yeah. Good question.
Shall I? Would you like to? Oh, that's a completely different. That's not what we do. We are experimentalists. There's many people indeed who work on quantum software. There's a large institute in Amsterdam, QSoft it's called, and they try to develop indeed specific quantum software. Not only developing algorithms. We've talked about Shor's algorithm. There's also other algorithms like Grover's algorithm, and Deutsch is also another algorithm. These are specific algorithms that people develop, but also there's code indeed for error correction, quantum error correction that's been developed. So all this software needs to be made. So there's a lot to do, and it's not only making the physical qubits, but also letting them talk to each other, and also thinking about large-scale integration. How can you control 1 million qubits? You probably need some kind of super control to have the control at the lowest levels. So it's clearly not trivial. Yeah.
Very nice moment to give a big hand to Floris and Femke, of course. Thank you very much. And a big hand for Alexander, who takes the place of Floris.
So Alexander, at the beginning of this year, I saw all these videos coming on Instagram about Majorana 1. Did you see those as well?
Yeah.
So did you see them? Yeah, it's a bit sticky. I'm sorry.
So myself, I'm not so much on Instagram, but can you show them?
Yeah.
Because I've heard it's quite a hype.
Yeah, it's quite a hype. Okay, so here we have 3 of those videos.
This is the most powerful chip ever created. And this right here is the coldest place in the known universe. This is the Majorana 1. Microsoft's revolutionary quantum chip. Nearly 20 years in the making, this breakthrough didn't just push the boundaries of computing, it redefined them. That's because this is the world's first quantum processing unit powered by a topological core. Designed to scale to an unprecedented 1 million qubits. In other words, Microsoft didn't just build a new quantum computer. They created an entirely new state of matter. That's not a solid liquid. It's a state of matter that has only been theorized. That is part of the breakthrough observing and controlling Majorana particles, unlocking more reliable.
Okay, that's going really fast. It is a big hype. But I've heard stuff like a new state of matter. What is that about? Can you explain that?
I think a new state of matter, like a gas, liquid, or solid, that might be a bit too strong formulated. But we can think of it more as what we know about conductors, insulators, semiconductors. So they were already talking about this topological insulator. And that's actually what this chip is based on. Let me skip real quickly. Yeah, so the topological insulator. And this topological insulator is based on a mathematical concept called topology. And that's the mathematical concept based on equivalence of categories. Okay, so what does that actually mean? It means that a donut can be the same as a cup. Okay, that doesn't really clear up anything for me. It says you can transform a donut into a cup. Well, and it also says that a donut and a cup are not the same as a sphere and a, yeah, how do you call this actually? In Dutch we call it a krakeling, but and what's the difference of these 3 objects? That's actually the number of holes. So what we call the number of holes here the equivalence category. And we have another example of this topology and equivalence categories. So that's these Dutch islands over here. So we have Terschelling, Ameland, and Schiermonnikoog, and we have 3 spots on the map here. So we have spot A and B, they are on the same island, and we have spot C on Terschelling. And we can say that A and B are topological equivalent to each other, while the spot C is topologically inequivalent to A and B. And that's because the equivalence category here defined is being on the same island. So to go from spot A to spot C, we have to cross the C, and that's where the topology is broken, actually. Now, okay, what does this have to do with material science? How does the topological insulator here come in? So there we have to look at band diagrams. So this is a material property that we know from semiconductors. So a semiconductor on the really, really microscopic scale can be described by a band diagram. So all these bands, you don't have to know what this all is, but you can remember that there's this gray band over there. That's what we call a band gap. And now this band gap, or these two band diagrams, can be topological equivalent if they can be transformed into each other without closing this gap. So here we have two of these band gaps on the left and the right, and they are color indicated. But we see that if we want to cross from this left band gap to the right band gap, we have to cross through a critical point where the colors match each other. So that's what you see in the middle. There's a critical point where we have to close the band diagram and close the band gap to actually transform these two band diagrams into each other. And that's what we call that these two band diagrams are topologically inequivalent. Now, how can we use this for material science? So if we connect two of these materials with different band gaps, then at the interface, so for instance here we have topological insulator connected to vacuum, so just air or what is around us, or nothing, that's actually what the vacuum is. Then we have two different band diagrams, so the topological insulator has this inverted band gap, and the vacuum has a regular band gap. Then at the interface, we have to cross. We have to connect the red part of the band diagram to the other red part of the band diagram. So we have this cross in the middle, and that actually leads to conducting states on the surface. So on the interface, we have conduction. So electrons can flow here, whereas in the middle of the material, there's no conduction or no current. And this leads to even more special properties if we look to this in 3D, so in real material science. Then we can actually have that the spin that Floris already mentioned of the electron, so if the little magnetic field is up or down, is connected to the direction of the electron that it's moving. So we can think of this as a highway of spins. So all the spins that are going on the left of the material are going like this and are spin up, and all the electrons going on the right of the material, those are spin down and moving in that direction. But I heard another thing in the video as well, Alexander, and I'm very curious to your opinion about this. I can show it.
So for this chip, they're not building it from electrons. They're using Majoranas for computing, which is an entirely new particle. It's actually half of an electron.
So they're not using electrons, they're using Majoranas. What does that mean?
Yeah, that's maybe not completely true. So they are still using electrons. And the electrons on a chip have interactions with atoms and all other electrons around them, with the superconductors that we will discuss later. So these are still electrons, but they get other properties because of the interactions. But she mentioned something special, that the Majorana is like half an electron. And there we get very close to now what is a Majorana. And historically, we go all the way back almost a century to a paper by Dirac, where he discusses the electron. This is a very famous paper on the nature of an electron. But what he actually tried to do in this paper, and he worked on this for a very long time, is to combine the existing quantum physics they had developed at that time. For example, the Schrödinger equation was a very famous differential equation in which you can show how the wave function develops as a function of time and position. This was known physics. And Einstein had a relativity theory, special relativity. But the combination of those two together, this was still a big puzzle. If you know a little bit relativity, there's a square root somewhere, and if there's a square root in the differential equation, the mathematicians will know this is very hard to solve. So he worked very hard on trying to solve this combination. And then, as the story goes, in Cambridge, he was in his college staring into the fireplace. When he got the insight that maybe a wave function is not a function like a sine or a cosine, something like this, but maybe it has multiple components. And once you put the multiple components in, then the mathematical structure became solvable to him. And actually, he tried with 2 components. It didn't work. He tried with 3 components. Also took him a year. Didn't work. But finally, he looked at his wave functions, and they had 4 components. Femke and Floris discussed already spin. It turns out that the first 2 components, and the second, the third, and the fourth, are combinations of 2 spins. This is how spin enters as a very mathematical construct into this theory, combination of Schrödinger and relativity. But what was more, he discovered that the first 2 components, they describe something at the positive energy, and the bottom 2 components were at the exact opposite energy. He called this an antiparticle, as if there was the electron that people knew already, but that there was also an anti-electron. And this is, of course, what we now know as the positron. It just came out of his theory as a prediction, and later it was verified that this is the case. And it turns out that many particles have their own antiparticles. And a Majorana is a particle that is its own antiparticle. And this was predicted by Ettore Majorana. Majorana was a very clever student with a lot of mental issues. But he was very clever, and he wrote this beautiful paper. After being ill for a long time and having been expelled from Germany, there has been a lot of articles written on that, but he was clever. In the lab of Fermi, he developed this theory that there is an additional solution of particles and antiparticles that are the same. And this was just a theoretical construct. It didn't have a meaning. He thought that maybe the neutrino, another particle, could act like this. Probably is not the case, but that's what he predicted. But that's where the name Majorana state comes from. It's named after him. His personal life, it's very strange. So this he wrote in 1937. In 1938, he disappeared. He took all his money from a bank, but then he was not seen again. So some people claim he committed suicide. Quite recently, they analyzed some old newspaper photographs from the 50s that were taken in Argentina. And with modern face recognition software, people claim that the middle part, which was taken from this photo on the newspaper, is the same as the original photos from Majorana, proving that maybe this theory that he went to Latin America and lived there for quite a while is true. We don't know. The Italian government just closed the investigation, so they don't know. So the particle is its own antiparticle. It's there and it's not there. Majorana, you see that? It's there, it's not there. Anyway, this is the Majorana state. But Femke, what does it have to do with your story about this topological insulator?
Yeah, so where does this topological insulator come in? And therefore we have, again, to look a bit at the mathematics. So the video already gave a little takeaway. The Majorana is half of an electron. So we can look at a chain of electrons. And if a Majorana is half of an electron, then we can as well just draw all these Majoranas in these electrons, right? So the 2 of these Majoranas make 1 electron. But why wouldn't we just shift these electrons and redefine the structure? So now we still have a chain of electrons, but we have 2 Majoranas at the ends isolated. So you can see here the difference of these two chains. Here we have a chain of electrons in the bottom, but at the top we have two Majoranas isolated. And this is where the topological insulator comes in. So this is the mathematical construct, but if we design something that's one-dimensional, so for instance the topological insulator with this highway of spins, and we combine this with a superconductor, so the same superconductor, for instance, as Floris and I discussed in the first part, then we can make a structure where these Majoranas are actually isolated from this one-dimensional structure. That at the ends of a one-dimensional structure, for instance, a nanowire, the Majorana would appear. But how can we use those Majoranas then actually for quantum computation?
Yeah, so that's still the missing ingredient, right? We now know what a Majorana is, and we know how to create it, but now how can we do a quantum computation with that? And that's in fact what's called braiding. Braiding, or in Dutch gewoon breien, is moving around particles around each other, or ropes, and make a structure. So why would that be a quantum computation? And there, the concept of braiding is basically moving something around something else. And if you do that in nature, if you take two particles and you move them around each other in the three-dimensional space where we live, not so much changes of this particle. You can think of it yourself. If you take a coffee cup and you move it around in this room, it's still in the same position afterwards. Nothing changed to that coffee cup. In two-dimensional, and that's depicted here, even if there are two particles, you think you move it around it, but if you change the orbit a little bit, you move it below it, and it's the same as doing nothing, basically. Nothing changes to these particles. And this changes in two dimensions, in flatland. If there's a particle, and you move another particle around it, you can make a clear distinction, whether it went around it or not. Yeah? Now you can see there's no deformation possible that one suddenly crosses over in the other. It turns out that if you do it this way, and if this particle in which you move it around has some special properties, you can change the quantum state of the system. Strange, right? I see you. Shall we demonstrate this?
Yeah, let's demonstrate.
Does Peter allow us to do a quick experiment? No water?
Yes, so it's again this thing, but there's no water inside or lemonade.
Okay, I told you if I move around an object in 3 dimensions, nothing happens. But I can mimic 2 dimensions by putting my arm now, attach it to it. Mathematically, you can show that this effectively becomes 2-dimensional. If I take this object, and please look at which way it points, and I start to rotate it, I've now rotated it by a full circle. You see that? But you see, the object has changed, right? Look at my arm. But what if I continue another rotation? Now it's back. It's matching, huh? You can try this yourself at home.
I have an idea. We can do it ourselves right now. So if you can stand up, please, then we can do an experiment with all of us. Okay, here we go indeed. So, okay, I want you to point your hand flat upwards. And now we're going to turn our arms without actually turning our arms. So now we're going to move our hand upwards, then to the left, and then again to the front. Now you've turned your arm without actually turning. We can do this again. You see? We've now made 180 degrees. We can do it again, but it gets more harder. It gets harder and harder. Now it's not even possible anymore.
So we are not actually doing now a quantum computation, but we get very close to this. Because this turning around of objects has a special feature once you do it with this Majorana states. And there you have to believe it, that this becomes the speciality. It has to do with this 2-dimensional nature and the phase that you pick up along the way. And this is basically what Majorana worked on. If you interchange 2 Majoranas, basically you pick up a phase. There are special Majoranas that if you do it in a certain order, the total quantum mechanical wave function that you get depends on the order in which you interchange the particles. And that is a very robust way of changing a wave function that is not so sensitive against noise. If you think about some electromagnetic noise on electrons, okay, they can wiggle them around or change the spin a little bit, but to change the position of two particles, that's of course a very strange noise. So the computation is done by interchanging these two Majoranas. And just as an example, it's a bit schematic here, but you can think of a T-bar in which you have multiple Majoranas. And Majoranas, as said, they can be there or they can be not there. They're their own antiparticle. So let's say we start in the state that they're empty. They're empty Majoranas. But once you move one of them inside the T, and then move the other one to the other side, you see, you start to swap the two middle Majoranas. Initially they were empty, but you can mathematically show that if you do this procedure, it looks the same afterwards, but in fact now they are half empty, half full. They are in a superposition of 0 and 1. By just interchanging the two middle Majoranas, I've created a superposition. There's another one in which I create entanglement. There's another one in which I create a gate that inverts the bit. So there are all kinds of gates possible just by braiding these two Majoranas.
This all sounds very nice, but how far are we actually now? Because Microsoft already claims they have found this Majorana and that they can work with it, but how much is actually true about this claim?
So, okay, the whole Majorana PR around it, they present it as if they had millions of qubits. This is not true. They made a kind of readout device, so it's not even a single qubit. This is to temper a little bit the expectations. So compared to the discussions we had with Floris and Femke of where quantum computers are, which technologies are running ahead, this one is by far lagging behind. But once they can make the hardware, of course, it could be a robust way of doing the computation. So Femke, can you show us a little bit what you did in this context?
So now we come back to Peter's question actually. So what do we do and how does this apply to the Majorana research? So here in Twente we make nanowire devices. So we start with these tin telluride nanowires that Floris already mentioned, but also all kinds of different materials we research, and those materials are grown usually in Eindhoven for the wires, but also in Twente ourselves we grow some materials, but then not wires, but thin films. But my research was focused on the wires, so that's why all the PowerPoint animations will now be focused on wires. So we start with a growth chip with all these upright standing nanowires, and we can pick those up with a micromanipulator needle, and we lay them flat down on the substrate chip. Now, in PowerPoint physics, this of course looks very nice, but to give you a bit of a realistic impression of how this actually looks like in real life, I show you now microscope images. These are already 1,000 times enlarged compared to what you can see with the naked eye. So here you see the growth chip, so the ones with the upstanding nanowires, and you see these small spots which I've now indicated with circles. Here I've removed actually thousands of these wires, and I've put them down here on the right. You see some gray dots over there. Those must be nanowires. If we should believe the microscope image, it looks more like dots. But if we look in a more high resolution image, so here you see on the right it's enlarged by, on the left, sorry, you see enlarged 2,000 times. So instead of 1,000 times, 2,000 times. You already see a bit that the wire is lying there, but if we enlarge it even more, so 14,000 times, then we actually see that we have deposited one of these wires. So then again, in PowerPoint physics, we have this wire laying on a substrate chip, and what we then do is we define in the computer, we define where, in which spots we want our contacts to be, to do these experiments. And we then make these contacts, and we can actually do multiple configurations of contacts. So we can all make these exotic configurations, or we can try different materials, for instance the superconductor that we actually need in combination with our topological insulator to make these Majorana states. But if we look in the microscope images, then you see that these pictures all look like this. So you have this small nanowire and all the different contacting recipes that we've tried. Now, after we've made such a nice device, then we also want to test if we actually have found this Majorana, of course, or if there's interesting other physics. We are very interested in just fundamental science, so that also motivates us. So we put this chip, which is pink here, or purple, and we make bonds. So we connect it to a PCB via these small wires, and we put it in a cryostat. So this is what it looks like in real life. Here we have the chip again, and you see these small wires going to the chip. And then we can make a connection to this dilution fridge, which is colder than the universe. And this is actually what they state at Microsoft as well in this video.
Now the wild part is to get this new state of matter, they need very specific conditions that this fancy freezer is able to deliver. It takes about a day to fully cool, but it's able to get down to 50 millikelvin, which is about 10 times cooler than interstellar space.
So Microsoft is doing very cool about this, but we actually have multiple of those freezers in the lab here. Yeah, so with that, I think we come to the end here.
But I think this is also a bit our conclusion. You can criticize Microsoft for overhyping this field. On the other hand, they create a lot of attention to it. They have a good PR, especially they hire a lot of influencers. That's what they do very well. But aside that, they have 200 physicists working on a dedicated problem trying to get this working. So, of course, our teams are smaller. We're also trying to compete, but in some sense, they push the field, and I think that's also quite okay. So the Majorana chip, it's a hype. There's not even a single qubit, but maybe in the future, it could be a robust way of doing this computation.
Yeah, so the fun is only starting now, and you can also participate in doing quantum yourself. So for instance, by going to qiskit.org, you can try out working on a quantum computer of IBM and already try to work with these quantum gates, and you can even get certificates or compete in competitions and all these kind of things.
The first 10 minutes are for free, but you can do a lot of computations within 10 minutes, and afterwards it's $99 per minute. So.
But still the motivation to do quantum yourself, of course.
Thank you.
Thanks.
Thank you. So, thank you so much for the great explanation. It's a bit mind-blowing sometimes, but I try to imagine a particle which is its own antiparticle at the same time. That's still very difficult to understand. But to start, one question to clear up things a little bit. You have fermions, bosons, and anyons. And anyons are two-dimensional particles, or could you perhaps explain a little bit more about those anyons?
I tried to be a bit fast there.
Yeah.
It wasn't a slide.
Okay.
So in 3 dimensions, I told you that if you move things around each other, nothing happens. But it's not completely true. The wave function can actually pick up a minus sign when you do this. But in quantum physics, if you want to know what comes out of a measurement, it goes always with the wave function squared. And then you lose the minus sign. So observations are the same, so that's why it looks the same. But those particles that actually pick up a minus sign when you interchange them, these are the fermions, and these are electrons, quarks, protons, neutrons, etc. And the particles that do not do this, that do not get the minus sign, these are the bosons. And these are the photons or the Higgs boson, gluons. These are particles that do not pick up this phase. And then in a flatland, in 2D, you can have mixtures. You can pick up this phase. It can be any phase between 0 and pi. That's why these are called anyons.
I see, yes. Yep. Okay, great. Thanks. Probably there are some more questions around here. That's a good question. The highest temperature at which do quantum computing?
Well, so the photonic quantum computers, they run almost at room temperature, right?
I will go over here. You're from the photonic quantum computers. How warm can they become?
The effective temperature of photons is thousands of degrees. So if you're at room temperature, you're basically cold for photons. So a photonic quantum computer runs at room temperature.
But then to detect Pepijn's photons, you need a cooler, a very careful detector. So there's always some cryogenics involved, but strictly speaking, quantum can also work at room temperature. Yeah.
Okay, but a quantum computer, you need to cool down things. So
Well, to read it out, especially the photons,
Yes.
you have to need single photon detectors.
yeah,
These are very often using superconductors.
yeah,
Those have to be cooled
cool down.
Yeah.
Yeah. So in the
to be
end,
sensitive.
you
But
end up with a big cooling device. I was wondering, perhaps some of you can answer this question. How much energy does it cost to do a quantum calculation? Because flipping an electron or something, I think that's very, very minor in energy, but cooling down this whole thing to temperatures which are cooler than the universe might take a lot of energy. Can you say something about this energy usage?
yeah, so
Maybe we start with a photonic quantum computer. That's doable, I think, or not?
So actually the king asked this question to our spin-off company, how much power that machine uses, and the answer was, well, maybe 2 kilowatts, something like an iron, which is mainly for the cooling of the detectors. Yes.
And the Majorana machine from Microsoft is
same. And anything you want to cool down, you need a 10 kilowatt cooler.
okay.
So that's, but it's not necessarily like what you think of AI, that dissipates a lot of energy doing the calculation itself.
Yes. Yeah.
That's not necessarily happening here, because in quantum mechanics, you want to avoid that this state decoheres, collapses, and that is dissipation.
Yeah.
So strictly speaking, all those superconductors, the electrical currents, they run for free, basically.
Yeah.
So the actual computation is not taking the power, it's just the cooling.
The cooling. Yeah. Okay. Thanks. Let me see.
Yeah, so there was a graph, it might have been in the first presentation, I've forgotten, but there was the 3 times 5 is 15. But how did it actually work? So can you maybe describe what the computer did to achieve that?
So we can look up the graph. And then
Belgian
Floris
guy.
can maybe
This
answer this debate.
PhD calculating 3 times 5. Let's see.
On the my microphone?
Yeah.
it's on.
Yeah.
So
Coming
this one,
going.
right? This graph, yeah.
Yeah. How does this work?
Okay, I haven't done this experiment. So if you click once.
Yeah.
So the only thing I know is that this was done with an incredible amount of pulses. And what you see here in this graph behind the 15 equals 5 times 3 is all these sets of pulses. And with these pulses, they try to address individual nuclei. What you see in this cartoon in top, there's this 7-qubit molecule. So it's a molecule that consists, I think, of 12 atoms, and they all have different nuclear resonances, just like in MRI. These all have their own resonance frequencies, so they can individually let one nucleus spin or another one spin by using different frequencies. And if I look at these pulses, these look like indeed different ESR frequencies of the corresponding to a specific nucleus. So they let these individual nuclei rotate, and that's actually controlling the qubit state of that nuclear spin by rotating those spins. So then they have these 7 nuclei, they all put them in some kind of qubit ground state, and then from that ground state they can then try to rotate to different superpositions. And then they use those states, those nuclear spin ups and spin downs, to get these 7 qubits. And then you need to perform the quantum gates. So that's quantum gates means that you, for example, start in a spin down, and with some kind of pulse you can rotate it to by a quarter or a spin up. And then that's the quantum gates you need to have. And then finally, with the combination of quantum gates, you can somehow perform these actual calculations. But for that, you would actually need to know how this Shor's algorithm works. And honestly, I'm not a mathematician, let alone a quantum mathematician. So if there's anyone who understands how and why Shor's algorithm works as it works, then I'd be very interested to get a 2-sentence explanation. But I think it's it's extremely complicated. So that's this quantum software that I think you asked about earlier.
Yeah. Anyone who knows this Shor algorithm? Good videos on YouTube. That's always a good solution.
Yeah.
Yeah. That always
Yeah,
works.
great advice. Use
Yeah.
YouTube. Yeah.
Look it up on YouTube. Okay. I had one more question myself. Could you say something about the group in Delft? They also discovered the Majorana particles. At least they thought they did. Could you say something about this group? How are they doing at the moment? Are they competitors of Twente in Delft?
So this is recorded, right?
We can turn off the recording if you like.
No.
So the nature papers from Delft are both there and not there.
They are Majorana papers.
Seriously, so they're doing a great job. They had fraud issues.
Yes.
So some of the data was frauded. So those papers have been withdrawn. But even more fundamentally, it's quite difficult to prove that something is a Majorana. So already in 2012, they had indications, and in the paper they called it signatures of Majoranas. And that was a good scientific way of describing what they saw. And later, if people then come up with alternative explanations, this is how science works, right? It's also nice for us because then the race is open again. Of course, Microsoft is already making claims in the newest papers. But really, to prove it's a Majorana, that's already difficult. I think the proof will only come when people start to do this braiding. And that you show that actually the wave function is different than it is for for fermions and for bosons. And that's one of the holy grails at the moment. That's what people are trying and pushing.
Okay, I understand. Thanks. And one question, just to clarify things. I think you mentioned Majorana, a quasi-particle. What does that mean? A Higgs boson, that's a real particle, isn't it? And an electron is a real particle. But what's a quasi-particle? That's a particle and not a particle. Can someone help me out?
That's maybe related to this collective behavior. So it's like this Kitaev chain, so this chain of electrons, where multiple electrons are actually working together to create another particle, and that's what we call a quasi-particle.
Okay, I'll chew on that one. There are more questions. I'll get up.
Maybe to have a simpler allegory, like millions of water molecules together make up one wave, right? That's like a quasi-particle. It's one wave, but it's millions of water molecules that work in phase.
Yes, that's a clear analogy. Thanks. Okay. Go ahead.
All this is very interesting, difficult to understand, but in the end, of course, you want to have a mega computer which you compute faster data. But what is all what you are now trying to do with these nanowires, etc., will in the end create a calculation tool?
Thank you.
Good question. And I think if you ask us, we are basically scientists. We want to understand nature and see how we can tweak nature and let it do stuff for us. The development of actual making quantum computers will be mostly technological. Scaling it up to larger platforms, millions of qubits are needed before you actually have really useful devices. But already the 1,000 qubit processor of IBM, so every year I challenge the students to try to come up with algorithms and prove that they're already faster than the classical algorithms. So it's not yet the case. But they can show if you extrapolate the trends, then maybe in a few years' time this will already take over. And it's not that they are faster computers in the sense that they can do all the stuff we do in our phones faster with the quantum computer, but there are specific sets of problems that are very fast on the quantum computer. So Google, for example, there's a very fast algorithm of seeing if a word is in a database or not. Well, that's Google's business, right? So that's why they are interested in quantum computing. Or if you want to mimic something that is inherently quantum mechanic, like medicines, like you described, that has to be modeled with a quantum computer. But even a mailman, what is the fastest way of delivering the mail? That already gets complicated quite quickly. And classical computers at some point, I think beyond 40 nodes, cannot solve it anymore. And this is also what quantum computers are good at. And there we actually start to approach the point where already the IBM quantum computer is almost as good as classical algorithms.
And maybe to be a bit clear, so we talked about quantum computation, but in Twente we're mostly doing fundamental research. We're trying to make new prototypes. So think about the analogy to the transistor. We don't know yet which type of transistor or qubit transistor will be the real building block of a quantum computer, if it will be there at all. We're playing around with our prototypes, we're doing cool physics, and maybe one of our prototypes will be used in a future quantum computer, but we don't know, and we just enjoy the ride and do these exciting experiments, and yeah, that's where we're at. And the bigger story is that there's also an exciting prospect, but we're not the engineers indeed who are trying to couple 2 or 3 or 10 qubits to each other.
No, because these nanowires that we've shown here, that will probably not be in a quantum computer itself. There will not be some kind of labor act where people will manually put these individual nanowires on the chip and designing all these circuits.
We need 1 million.
Yeah, so for 1 million indeed of these qubits. So that will probably not be the case, but it is interesting for the fundamental part of it to research what these materials can do and to make the step towards technological applications. There we need different systems actually.
And I'm curious, did you buy this Microsoft Majorana chip and take it apart in the lab?
It's not for sale.
It's not for sale, because if you look at the video, it seems like you can buy it at the grocery store. But how then, Alexander, you said very firmly, well, they claim to have 1,000 qubits, but in fact they only have 1 or 2. How do you know that? But where is this knowledge based on?
So on their scientific papers. So they have a lot of PR in which they claim fancy stuff, but in fact it's not them claiming it, it's the influencers saying it.
I see.
That's their safe way out. But if you read the scientific papers, there's no claim whatsoever about even making a single qubit. So they're careful, and they do good science, but it's not millions of qubits as the influencers say.
I see. Yeah. Okay, that's clear. Thank you. I go up. Let me see if I can do this. I feel like walking through a labyrinth, like a ball, but I found not the entrance, but the right person. Go ahead.
Do you think the quantum computer will ever replace the computer as we know it?
No, so as said, I think the quantum computer is a solution to, or develops solutions to very specific problems. So it will not actually replace the computer, because there are also certain problems that the quantum computer is very bad at to calculate actually. So it's more like a new type of computer in addition to the computer as we already know.
So people currently think it will be something like in the cloud, that you can use it online, just like you use AI, which uses these data centers, and you will not have a handheld quantum computer. At the same time, IBM, Watson has said 30, 40 years ago, I think there's a worldwide market for 5 computers. And I think that's, you never know, right? So,
So maybe we have a quantum computer in our pocket. I think, Femke, you already also mentioned climate modeling can be done with a quantum computer. Why is that the case? Because it's a natural process with a lot of complexities. That's also typical.
It's a very heavy computation to do, and these heavy computations, those could be optimized on a quantum computer.
Yeah. Okay. And I liked your chessboard metaphor with the rice. Well, if I understand correctly, if you have an ordinary computer, you have 1 rice dot on the first square, 2 on the second, 3 on the fourth, 4 on the fourth, 5 on the fifth. But for quantum computers, it's 1, 2, and then 8, and then that's going exponential. That's the
8,
difference
16,
between ordinary computing and quantum computing. Yeah, that was a very clear metaphor. Okay, I think it's almost time. Maybe there's a final question up here. Yeah, you have another one? Go ahead.
What are the examples of problems that a quantum computer in your eyes cannot do?
Gaming or something like that.
So a well-known example, which is maybe not so useful, but I think either the Deutsch-Joscha or the Grover algorithm, it can search quickly through databases. And the canonical example is a phone book. Now, we don't have phone books anymore, but normally if you'd go through a phone book, you would go through the city where someone lives, and then look for the name, and then you could find the phone number back in the days, remember? I think there's a few people here that may remember still phone books. Otherwise, look it up on YouTube. But this quantum computer can search quite quickly through these large numbers, and you could give it a phone number, and it would find the phone number in the phone book. Right? So I think that's the example that I've always heard, that it can search quickly through large amounts of information, which is also similar to, indeed, handling great amounts of information to predict climate physics or something that easily explodes exponentially, where quantum computers have a better way of handling specific information sets. So it's not all information. It will not help you to do your word processing or your Excel processing quicker. Definitely not. But specific solutions that are complicated, that increase exponentially, can be solved better by a quantum computer. Sorry, what cannot do? Oh, apologies.
Yeah. What are quantum computers really bad at?
I think the maze we try to show as an example is also, I think, a good example in the type of question you can ask. Is there a solution to the maze? Then water gets out at the right exit. But you don't know which path it took. So if you want to if you want to calculate the actual path it took, that is not that algorithm suitable for. But if you want to answer the question, is there an end of the maze or not? Yes, that's a good question. You see, so in that sense, algorithms can easily be split into good algorithms for a quantum computer that you can massively parallel calculate, or the ones that you need serial calculations for to get your actual answer.
Okay. I think we have to round off. If you have any more questions, please come down and ask them afterwards. This was one of the most complex lectures I ever hosted and moderated. But it was a fascinating evening. We learned a lot. Perhaps, Alexander, you can do one more time the trick with the heater. I don't know what the heater is in English.
Remember, if you do it at home with your...
Do it slowly, because you did it very fast, and maybe we can still to get an idea about topology. And
just rotate it in a certain direction.
Yes.
Go all the way around.
Yes.
This is 360 degrees.
This hurts your arm.
It's different, and normally it should be the same. But now if you continue, and now if you put it under your arm, that's the trick. You still rotate it in the same direction by twice 360 degrees, and only then it's the same again. So this is the 4-pi periodic nature of these Majoranas.
Yeah, so at home you can impersonate now a Majorana. Impress your friends and family at home. Yeah, I use this, or what was your other trick, Femke? We start like this. I'm a Majorana.
Thank you very much.